disrupted. Anyway, so the sound waves. Well, so far we learned about a sound wave will be it is a longitudinal wave. And we learned that the speed of sound, it depends on medium. So 340 in air, 1500 in liquid, and then 3000 meters per second in solid. Usually is that I memorize 340 first in air, and then if you make it like around 10 times bigger, that will becomes the solid. And then you reduce it by half, then you get the liquid. Well, and then afterwards, we also learned about like frequency. Then for sound, what does it affect frequency? Well, it will affect the pitch. You learn it in integrated science. Then how about the amplitude? Well, amplitude will affect the loudness of the sound. Now talking about sound, we have so many different musical instruments. For example, a guitar and a guitar and a piano. Well, you can play the same frequency. For example, the do in piano and in guitar or in violin, they have all do and re fa sol la ti do. So let's say you play the same tone, do. It means that it has the frequency of certain hertz. But of course, the do in piano and the do in guitar, they are not the same. They sound very differently. So what is that kind of characteristic sound produced by the musical instrument, even they have the same frequency? It is so-called the wave form, not fronts, waveforms. Waveforms, we talk about like the different sensation or the characteristic of the sound made by the musical instrument. Well, it just means like this. For example, a pure tuning fork will have a do like this. Well, however, if you like a guitar, then it may have like this. No, sorry. So they may have something like this. Like this. Well, never mind. I just repeat it 3 times. So after all, you still have the same wavelength or same frequency. From here to here, 1 period. From here to here, also just 1 period. So that means you have the same period, same frequency, same pitch. But because the shape of the wave is different, so therefore you will hear different types of sound. Usually the tuning for the ding, that kind of sound will be this pure sinusoidal wave. But when you play a violin, a piano, actually they do not produce this kind of pure sinusoidal waves. Well, then, to elaborate further for sound, we'll learn something called the spectrums of sound. So there are 3. There is first of all, well, we are human, so human-centered. We start with the audible sound. This is the sound that we can hear. Audible sound. Well, to specify sound, essentially we just specify using frequency. The one with 20 to 20 kilohertz will be the audible sound. beyond that, then it will be the ultrasound. Will be above 20 kilohertz. Well, below that we have infrasound, lower than 20 hertz. Well, where we find them? Well, infrasound we find in whales, in elephant. Ultrasound we find it in the bats, mouse, things like that. And this is human. Well, you kind of wonder, well, why it seems like that the living organism being smaller, then they can produce a high frequency sound, while for animals that are bigger in size, they produce a lower frequency sound. We'll actually talk about it. Like this. We'll talk about this later. But we need to talk about some application. For ultrasound, we can use for, of course, scanning the baby. Application. Amplification. Application. Well, we can use ultrasound for scanning baby. Or also you can scan the seabed. It's because they got a ultrasound. First of all, you use the ultra. I'll talk about how to scan it later first. Scanning the baby and the seabed. Well, infrasound will be used to study the inner core of the Earth. So it's something like, for those people who want to study earthquake, they will use the infrasound to study what is happening underneath. The audible sound is for us to hear. Well, how does it work? Basically, we use something called pulse echo technique of sound. What does it do? Is that essentially you have a surface, some reflecting surface. And you have a device, we give a name, call it transducer. Well, if you don't want to learn the name transducer, you just understand it as something that can emit and receive sound wave. Then what you do is actually you just shoot a pulse to a reflecting surface and it will come back. So this is so-called a transmitted pulse. And this is so-called a reflected pulse. Then on the transducer, what do we see is that there will be two pulse detected. The first pulse will be the pulse that when you send it out. And the second pulse is after the pulse has traveled and hit the reflecting surface and come back, that will be the second pulse. Like this. Usually the reflected pulse will be lower, will be weaker, but never mind, we just forget about that. Then in this case, we can detect this so-called time delayed. The time delay essentially is just the time taken for the pulse to travel from the transducer to the reflecting surface and from the reflecting surface to the transducer. So what's the point of doing this? Is that if we know the speed of the sound, then we can find the total distance traveled by just the kindergarten equation, speed times time. So speed times time dilated, that will be the total distance traveled. But for the case of ultrasound, remember, it doesn't matter of what kind of frequency is it. They will travel at the same speed in the same medium. Maybe I'll just put a remark here. Just remember here that they all have the same speed in air, for example. Of course, also in water, etc. So that means we know these values. Let's say the speed of sound is 340 meters per second. They get the time dilated, which is something you can measure using transducer on the screen. Then the distance between the transducer and the reflecting surface will be just half of the total distance traveled. So therefore, you can think about the thickness of the layer will be equals to just half of it. Then this is how we study how far away the reflecting surface is. We can do it. We can use this, for example, we can scan for scanning the baby, because you cannot look into the womb of my mother. You can use the ultrasound to scan it. Well, also you can study the seabed because it is so expensive to dive into the deep sea to study the seabed, but you can send ultrasound to the seabed and then let it reflect. So it's something like you have a ship, and this is the seabed, like this. And then what you do is that you just operate your ship slowly. Then you just send pulse and let it reflect. Then from the calculation, you can see, therefore how deep the seabed here. And move to another location, do it again. Location, do it again. They can have a good understanding about the structure of the seabed. Okay, and this is the user. Why do we use ultrasound? Why not use audible sound? Well, ultrasound will be so noisy. You will suffer when you are standing on the ship. Infrasound, it does not work somehow because infrasound, the wavelength is too long. We will explain later why. And why not using like microwave or other light to do that? Well, is it because water absorb all these electromagnetic wave? So therefore, we can only use ultrasound. But usually there is a storyline like, then how about like dolphins? Dolphin, they can hear the ultrasound. So therefore, it's actually when you really have the scientists using ultrasound in that region, the dolphin, they will all go away because it will be very noisy for them. But at least it's not a very big pollution. This is still okay. Okay, then this is about the spectrum of sound. We'll talk about the pulse echo. Well, and then the last thing I will talk about is the so-called diffraction. Well, diffraction is actually already one wave phenomenon already. However, it turns out that we do not learn much about diffraction, so I will also put this into put into this title about the basic understanding of waves. Diffraction. Or I will just take it as an application of the wave fronts. So for diffractions, what is happening is you have a wave coming by and it hits a gap. So this is the obstacle. And you have the wave coming by. I use this in, okay, just use this. Like this. Well, if there were no diffraction, I can still have wave to pass this gap, but only this part. This part, it does not involve any diffraction. It's something like non-diffracted. It will not be affected, so it's a still straight line. Or however, in real life, we know that even you're standing here, you will still be able to hear the sound or still detect the wave. That is because of the process called diffraction. So this part is the diffracted rays. And we represent it using circular line or curved line like this. So that when you are standing here, you can still hear the sound. Okay, how about here maybe? So therefore, what is really diffraction is it's just the splitting of the energy transfer when it passes through a gap or an obstacle. Diffraction is the splitting. Splitting of energy transfer. Why? Is because you can think about, remember the ray is perpendicular to the wave fronts. So when you draw this, perpendicular, perpendicular. You draw this here, you have perpendicular, perpendicular as well. So therefore it's a splitting of energy transfer. And this happens because it meets a gap. Or obstacle. Okay, like this. So what do we need to learn about diffraction besides learning how to draw the diffracted part and the non-diffracted part? Is that we need to understand when will diffraction be strong. To talk about how strong the diffraction, usually we will focus on the corresponding angle of the ray that is happening here. Does it mean talk about like how big is this angle? Well, there is a formula, but it's not in your syllabus, but never mind. I'll also include it because it will help me to explain it well. The equation here is theta is approximately equals to lambda over b. Lambda is the angle of diffraction. In radian, while lambda is the wavelength, of course. And the B will be the size of the gap here. What we need to learn here is to not do calculation, of course, because as I said, this equation is not in your equation book. However, this equation tells you one thing is when the wavelength is larger than the size of the gap, then the angle of diffraction will be large. While on the other hand, if the wavelength is much smaller than the size of the gap, then the angle of diffraction will be small. So this will be the understanding. So let me see. It's a little bit tricky, but never mind. Let's do this. So it's about this. So let's take an example. If the wavelength is much smaller than B, then theta will almost be 0. That means no diffraction. Well, what does that mean? A good example of this will be you use a laser beam. Laser beam, you shoot a laser beam to where? To a, let's say, to a window. Let's say this is the window. Like this. Well, laser beam has a wavelength of around nanometer. For red light, for example, 700 nanometer. Well, but the size of the window is about 1 meter. Well, these two lengths are so big or so large difference between each other. 700 nanometer is like 7 times 10 to the power minus 7 meter. So in this case, therefore, you will never see the laser will spread out like this way. No. It will just go straight and then no diffraction at all. Okay. Well, on the other hand, another example is when wavelength is larger than the size of the gap, then diffraction will be strong. One example would be, well, usually let me think about. Like this. And then usually in real life, in experiment, what we usually do is that you have a gap which is of a fixed size, and then what you do is that you produce a wave with a wavelength to be short first. And then what we usually want to claim in physics is, how do you say? Is it a little bit tricky here? The idea here mainly is, I want to say is, there are two things I need students to know. First thing is the wavelength. If the wavelength is too short, then the diffraction angle will be close to 0. It means that it almost does not diffract. Well, on the other hand, does that mean when the wavelength is much bigger than the size of the gap, then we can say the diffraction is strong? It actually is also not the case. Well, it's because when the diffraction is strong, then the energy will just spread out and it does not really contribute any observable measurements. Well, the bottom line is what we usually say in physics to claim that the diffraction is strong is when the wavelength is comparable to the size of the gap. This is something that we want you to know. Which is to say that the diffraction is strong or is most observable. When the wavelength is comparable to the size of the gap or the size of the obstacle. This is usually what we need you to know. So therefore, let's make an example. Well, our mouth. Well, you use a sound, for example, 1000 Hertz. And then in the air, the wave speed is 340 meters per second. We'll calculate this. It means that the wavelength equals to V over F will be equals to 340 over 1000. That means it's 0.34 meter. Oh, meter is too small. Make it one more. This one, like this. This is 10,000 is also okay because it's like 20 to 20 kilohertz. This is our audible frequency. So at the middle is around 110 kilohertz. So therefore, it will become 0.034 meter. Now what is this? This means a wavelength of around 3.4 centimeter. What I want to do now is to compare to the size of your mouth. Like this. Well, you're producing, and although sound is a longitudinal wave, but never mind, just make it like a transverse wave as a representation. So the wavelength is 3.4 centimeter. And then the size of your mouth, you can use a ruler to measure your mouth, is also just around a few centimeters, let's say 3 centimeters. So therefore, the fact that these two numbers are so similar comparable, then it results in strong diffraction. Meaning that, therefore, when you talk, you do not need to face to the audience or face to the listener directly. Other people nearby, they can still hear you. So therefore, that will result in a diffraction effect. So this is what I want to meet. Well, this is a really unfortunate thing, is that even in some other syllabus and other curriculum like the IB curriculum, they also cover this equation, but unfortunately the proof of this equation is too advanced for you. And so I think the key message is we should not the key message is for diffraction to happen, you need to have the wavelength and the size of the gap to be comparable to each other. Otherwise, diffraction will not occur and then you cannot see diffraction. Okay, now there's still another one too, it's called a spectrum of electromagnetic light. electromagnetic wave. But I suppose you can read the text for yourself. That part I don't want to go through it because it's not much storyline or not much explanation involved. Next time we will be able, and then now you can do the homework or the exercise set about the so-called the first exercise set for waves, and for waves, and I label it is as a general. And then next time when we talk about refractions, then we talk about the wave phenomenon. This is about the foundation of waves, and not yet the phenomenon. When you get to but when you really need to understand a phenomenon, we need to really fully understand this foundation first. But never mind, we finish here.